we do need to take an in-depth look and understand our signaling protocols for VoIP. So let's look at H.323. This was an IT/UT spec formed circa 1996. And the IT/UT said, hey, we've got this thing called ISDN, works really well. Let's just base everything on that. So H.323 is based on and still contains Q.931 signaling in its H.225 call setup. It doesn't need to be based on the layer 2 format because IP is a layer 3 only protocol. Layer 2 is handled by whatever layer 2 mechanism IP is going over, whether it's, PPP or Ethernet or HDLC or frame relay or whatever. Okay, so this can be used with any kind of POTS circuit, so that's one of the nice things. However, it needs a local dial plan in the iOS gateway, so this is referred to as a decentralized dial plan. The sub-signaling protocols, H.323 is really a suite of protocols. H.225 is used as TCP port 1720 as the destination port. Now this can be changed to UDP. Obviously, it would need to be done on both sides. There's an asterisk next to the H.225 because there's another form of H.225 called RAS, or Registration, Admission, and Status, which deals with H.323 gatekeeper call setup only, to and from an H.323 gatekeeper. And we will discuss this ad nauseum later in the gatekeeper section, not now. Okay, so H.245 comes after the H.225 setup, and this is used to negotiate the media, the DTMF relay, what codec we're going to agree on, whether VAD is going to be enabled or not, things like this. This is called the Capabilities Exchange. And this does something called Open a Logical Channel, or OLC, to define the media ports, IP ports that media is going to pass on, as well as the RTCP ports for the RTP to be controlled with. This also deals with flow control messages back and forth. And this uses the TCP port range from 11,000 to 11,999. And this is, well, I should say it uses that range when being used with slow start. And we're going to talk about the difference between slow start and fast start here in a moment. So taking a look, H.323 gateways, if we have a PSTN on the left, and let's just say, for instance, we've got a PRI, we've got our layer 1 framing and line coding, we've got our layer 2 Q921, and our layer 3 Q931, all of that occurs directly between the PSTN and the H.323 VoIP gateway, but it's terminated there. CUCM knows nothing about that. Now, talking back to CUCRI layer 3 based on Q931 and the H.225 based on Q931 obviously have a lot of fields that map to each other, but that's just it. The router, the VoIP gateway, is responsible for mapping those fields from H.225 to Q931 out to the PSTN, and when information is coming in from the PSTN, from that Q931 from ISDN to the H.225 Q931 fields on H.323. Okay, it's responsible for mapping, but it's not the same communication. And H.323 is a peer-to-peer protocol. It's not a client server. This voice gateway doesn't need anybody. It can exist on its own just fine and talk to anyone else. Has its own dial plan. It's an intelligent peer-to-peer protocol. And so there, in an H.323 gateway or trunk in my CUCM, I will never see that gateway, H.323 gateway, show up as registered. Won't see it, because an H.323 gateway does not register with a CUCM. Now, an H.323 gateway can register with an H.323 gatekeeper, and we'll talk about that, but that's optional. It doesn't have to do any registration. And CUCM is actually just another, believe it or not, it's just another H.323 gateway. It's providing gateway services between everyone that's wanting to talk from this gateway to all of its constituents, which happen to be IP phones, for instance, or maybe even another trunk. Okay, so CUCM is just another H.323 gateway. Now, I should mention in H323, there are actually 5 components. We really only use 2 of them today, maybe 3. Those are gateways, terminals, gatekeepers, MCUs, and proxies. So I'll go over them again. H323 gateway, that's what we have here. That's what we have here. We also have an H323 gatekeeper. We're going to look at that in a little bit. We have an H323 terminal. Now that is similar to a gateway, but instead of being a gateway to a bunch of more services, phones, DNs, numbers, whatever, it's a terminal. So it's really a gateway is also an endpoint, but a terminal is much more of an endpoint. It's like a termination, okay? There's only one person behind it, or maybe 2. So if we had that ATA 186 or ATA 188, the analog terminal adapter that we talked about, seems like 3, that would register with an H323 gatekeeper as a terminal. Okay, it only has 1 or 2 phones behind it, 1 or 2 numbers. So CUCM can actually register to a gatekeeper as a terminal, but that's not really the best representation because it's really more of a gateway to a bunch of other services. Okay, but again, H323 gateway, CUCM or the voice router, gatekeeper, terminal like an ATA, MCU, and a proxy. Now, an MCU is a multi-point control unit. Now, you might think, okay, so we still use those today, right? Like multi-point control units, MCUs for video conferences. Yes, but those are registered to CUCM. We really don't use H323 MCUs. Those would be when we had, and we basically didn't have a central call control like Unified Communication Manager, but we're, maybe we're back in 98, 99, and we're aggregating H.320, which is ISDN video conferencing, with H.323, which is IP video conferencing, and we're aggregating all these video conferences together, and we need a multi-point control unit. We can integrate that directly and control that directly from H323. But we really don't use MCUs with H323 anymore. We do use multi-point control units, but they're registered directly to CUCM for telepresence and other video conferencing. Another thing is a proxy. Okay, so gateway, gatekeeper, terminal, MCU, and finally proxy. H323 proxy is, again, something cube or a unified border element. Okay, so it can provide IP to IP services. It can proxy on behalf of, or think of it as a trusted relay point, really. It goes between, it relays between 2 endpoints that don't want to talk directly to each other for reasons of security or whatever. But again, we don't use it anymore. Why? Because we have Cube, IP to IP gateway, because we have trusted relay points. We have other things that can provide a lot more functionality. So we don't use proxies, we don't use MCUs as they are defined or related directly to H323. And we rarely use terminals. We don't put an H323 load on an analog terminal adapter, an ATA. We use Skinny or SIP, probably Skinny, and register it to a CUCM. Okay, so moving on. So the pros or advantages of H323, since we have to define a dial plan on every gateway for normal operations, well, then guess what? As long as we define them and plan them properly and efficiently, SRST has a ready dial plan for fallback. We don't have to provision an additional dial plan for SRST fallback. Because we can use things like voice translation rules and other forms of digit manipulation on each H323 gateway, we've got the availability for more granular digit manipulation available to us at the edge, either inbound or outbound. And we're going to use that quite a lot in our demonstrations. Every POTS type is supported, as well as something called MMOIP, something we haven't got to yet. Actually, those are the last 3 or 4 slides. We're going to talk real briefly, actually it's the last 1 slide, I think. We're going to talk about faxing, iOS on-ramp or iOS off-ramp gateway. And this deals with faxing, and an MMOIP is a multimedia over IP dial peer. So we have a POTS dial peer for plain old telephony system, VoIP dial peer for voice over IP, and then we also have multimedia over IP, basically email. We can email from dial peers. This is useful if we're taking a fax in one side and we want to turn it into an email. The router can do that. We'll talk about that. Also, another pro is if that we are at a remote site and the WAN link fails, SRST kicks in, we don't have any audio loss. The call doesn't drop. We might not have supplementary services. I might not be able to put someone on hold because my call control failed, but my audio, my RTP stream can stay up. This is something called call preservation, and we'll show you how to configure that. Really better than MGCP. Okay, I've got a lot more options that I can do in dial peers. So let's take a look at H323 call flow, and we're going to look first at slow start. So I've got my CUCM, I've got my voice gateway, it's going to be using H323, and then my PSTN. And I've got some form of TDM signaling represented down here by a gray dashed arrow in my legend box. Orange represents my H225 call signaling inside H323. Green represents my H245 media negotiation in H323, and yellow represents my RTP media. So to begin with, the call setup occurs, and it could occur in either direction. So next, the known as the originating gateway, or OGW, and this would be known as the terminating gateway, or TGW. So the terminating gateway is going to send back the call proceeding. And then that gateway will ring out to the PSTN. Once it's begun ringing, it will send back to the originating gateway, hey, I'm alerting the far side. And it's at that point that the CUCM, the originating gateway, begins playing back to its phone ringback. But not until then, not until we're sure that they're alerting. Let's say the PSTN then answers. Okay, so then the terminating gateway sends a call connect. The call is now connected. Now we need to negotiate media. So there's a capabilities exchange for H245. There's also a master-slave determination, one slave. Now, we're not talking about client-server. This is a peer-to-peer protocol. But for the rest of the media negotiation, we're going to try to negotiate back and forth. But what can sometimes happen with negotiations? They can break down, and we come to an impasse. If we come to an impasse, we first hold an election before we even begin really negotiating, basically to say, hey, one of us has to be in charge. We're going to try to negotiate, but if we can't figure this out, someone has to be the final say-so. So a master-slave election is held. Whoever becomes the master, if they can't necessarily agree on the parameters, then one side is going to determine what those will be, especially when it comes to the Open Logical Channel and the UDP RTP ports, RTCP. And then the RTP media ensues. Okay, so taking a look at H323 slow start, specifically H245 messages, we have something called TCS. This is the terminal capability set. This defines the codec, VAD, DTMF relay. The master slave, again, master is the final word if there's a disagreement. The open logical channels, OLC, I've already said this, negotiate RTP and RTCP. So let's take a look at the difference between that and now fast start. Fast start tries to get the media negotiated faster. It's the whole idea. So we still have a call setup, but now the call setup, the original message, contains not really a negotiate of the capabilities, but we're informing them. We're just kind of saying, hey, this is what we'd like to do. We'd like to do these RTCP ports. So we do all of that in the initial setup message. The terminating gateway sends back call proceeding, assuming that it supports fast start. If it doesn't support fast start, which iOS gateways do support inbound and outbound fast start by default, they use outbound fast start by default. Whoever is the outbound, the originating, sending the outbound setup, they're obviously the ones that determine if fast start is going to try to be used. CUCM has support for inbound fast start as well as outbound fast start. They're enabled mutually exclusive from one another on an H323 gateway or trunk by the tick boxes, but they're not on by default. Those boxes are not ticked by default. And also remember that an H323 gateway outbound, okay, when we talk about SIP, there's also something called SIP delay media, which is similar to H323 slow start. And there's something called SIP early media, which is similar to H323 fast start. With SIP early media in 7, so you might hear me refer to it in a few of the videos, in 7.0, it required an MTP to do outbound SIP early media. But in 8.0, although you still have to tick the box to use it, it does not require and it does not procure an MTP for SIP outbound early media, but that's for SIP. H323 still does require and actually procure or provision an MTP for outbound fast start, but that's just for outbound. So the way that it's boxed for inbound, and let's say the voice router, which does send out of it, so into CUCM by default, that does not require the use of an MTP. Okay, so the terminating gateway, the voice router sends back call proceeding. It rings. Then we have alerting. And then there's an answer from the PSTN. And then finally, there is the connect and our RTP media. Now that's assuming that the terminating gateway agreed on all the capabilities it was informed. Maybe it was informed of the codec G711, but the terminating gateway has a dial peer, not with voice class codec, but with a hard set default, actually G729 codec. Well, then it's going to basically say, no way, your fast start doesn't work for me. So we're going to send all that information early so that it doesn't have to basically sit there and go back and forth and negotiate. It's just like, hey, I'm informing you of what I'd like to do. If that doesn't bother you, then let's go ahead and just skip the negotiations and we'll just move on with things. And it actually is a lot faster start, although we're talking about, you know, milliseconds here, but still. And then there's also something not to be confused with fast start, but called early media. So let's take a look at this. So H323, again, CUCM. Now this is actually a subset of fast start. I do a call setup containing the H245, informing the terminating gateway of what I'd like to do. And then the terminating gateway sends back call proceeding. RTP media happens. Notice nothing's happened out to the PSTN media even before it sends a call setup out to the PSTN, because now it rings the PSTN and actually, yeah, ringing, and then we tell the originating gateway we're alerting, and then the answer comes, but media has already been going through. We send a connect, but media has already been going through. What's the usage for this? Well, this is, let's say mobile carriers use this. If I want to have like a specialized ringtone, not on my phone per se, but that the carrier actually provides, or some sort of important announcement, I can actually have the RTP media carry that specialized ringtone so that by the time ringing occurs, remember, here we go, RTP media came and then ringing came, so that when ringing goes, we basically override the default ringing that was obtained through the RTP media, or some sort of important announcement as soon as they come back. Another reason that this might occur, let's say I wish to, you know, the caller is going to maybe screen my call, and they want to hear me talking, but I haven't actually answered the call yet. So let's go back. RTP media comes, so my voice is coming through, maybe, potentially. Ringing, so now the call is ringing in, and I can actually listen to who's on the other side and anything they might be saying before I answer the call. And then I can choose to forward the call to voicemail based on what I hear or do whatever. Okay. Not saying this is commonly used, but Google Talk, for instance, which was originally, actually, I can't remember what it was now. But anyway, that supports early media where I can hear the calling party before I actually accept the call. So there are circumstances or places where this is used for certain. So that's H323. Let's take a look at SIP. SIP is an IETF protocol. H323 was an ITU protocol. ITU, International Telephone Union, you know, hundreds of years old. IET, well, not hundreds, but 100 or so. IETF, Internet Engineering Task Force, young relatively compared, so, you know, 50s. So anyway, the internet way of doing things, instead of building things from the telephony side. Okay, this is sort of more like the way Cisco approached voice. A lot of the carriers, Nortel, now defunct, Avaya, who was Lucent, who was Bell Laboratories, which is where my dad worked and where I got all my experience back when I was 5 or so. You know, they took everything from the voice side initially and tried to build IP into it, but Cisco acquired Celsius and they took the IP side, which they knew, you know, in and out, routers and switches, and said, hey, if it's going to go over IP, it's going to be critical that IP is of the most importance. So we can certainly learn the telephony side, and they build everything the other way around. So started with IP and went back into telephony. Okay. One of the reasons why obviously Cisco Unified Communications is a lot more stable, but didn't have as many features to begin with. If you look back 10 years, when I first 12 years, there were barely any features. You know, I mean, we had hold and transfer and a few things like that. And back then, if you transferred your phone to your own number, like if I transferred DN 1001 to 1001, it caused the CPU on the call manager in the little Windows box to just have a conniption fit, and it would totally crash because it couldn't handle, well, only once you called 1001, because it would just circle around 1001 to 1001 to 1001 to 1001. Anyway, but features came later. Telephony features came later, but it was rock solid on IP, provided that the installers knew how to do QoS properly. Okay, but anyhow, that's basically like SIP. Takes it from the IP side and goes back into building features to the telephony side. So there are more RFCs than I could possibly list for SIP, but the base RFCs are 2543. SIP was first around circa 1999, or first 7, but was ratified in 99. RFC 3261 and 3665 are some of the most important ones, if you care for some great bedtime reading. These are based on HTTP and SMTP-like messages. That's the messages for SIP back and forth. They're extremely easy to use. SIP is based on a lot of things already existing. Hey, time already exists as a standard on the internet. NTP, let's use that. So it uses NTP. DNS already exists and provides for robust services and failover and you know, prioritization with service records or SRV records. So let's use that. So it's based on DNS, or can be. So it's basically all the internet protocols that were already there. SIP said, why try to reinvent the wheel and do it all ourselves, kind of proprietary? Let's just cover the telephony stuff in our protocol, and everything else we'll use somewhere else. In fact, there was already something called SDP, the Session Description Protocol, which described media and was used for RTP. Well, hey, let's use that to describe the RTP media. Okay, we'll talk more about that. But the nice thing, just like H323, it can be used with any kind of POTS circuit. The default uses UDP port 5060, actually for source and destination, but it can be changed to TCP on both sides for connection-oriented and more reliable transport. It needs local dial plan in iOS, so it is still a decentralized dial plan. And it deals with something called user agents, a user agent client and a user agent server, so UAC and UAS. Server, the UAS, is the one sending a message at any moment, or that originally started the message. Okay? Then there is, this is basically how it does its peer-to-peer. There are two headers. There's the SIP header and the SDP header that I just mentioned. The SIP header is responsible for setup, teardown, and all the maintenance of the call, all the features, redirects, temporarily move, things like that. The SDP is an entirely separate protocol that isn't based around SIP, wasn't invented for SIP per se. Well, it wasn't invented exclusively for SIP, and can actually be used as a standalone protocol. We're actually going to see it. MGCP uses the exact same SDP protocol, but this describes the negotiation of media. It contains a lot more, such as we're going to take a look at in depth at it because it's important to know how to read it when it comes to your SIP debug messages and traces. And you're going to need that for your T-voice or troubleshooting voice exam. So looking at SIP gateways, again, TDM, if it's PRI or FXO or whatever it is, that terminates at the voice gateway. IP carries the rest. Now, there are some things in ISDN you'll see as we go along that don't translate to SIP. For instance, in ISDN, there are things called call type and call plan. Call plan is something like ISDN. That's the plan. Or private is another plan. There's also something called call type. There's 4 main call types that we use. There's more, but 4 main ones. Unknown, calling, and or called party. We have a type for both. Is the calling, is it the number? Is it an international number? Is it a national or long distance number? Or is it a subscriber or local number? Or is it unknown? We simply don't know. H323, since it's built using Q931, has a direct mapping for that and carries that information on into CUCM. But SIP doesn't, because it wasn't built with that kind. They didn't really try to carry or use Q931 in any way at all. So there is nothing that carries that type over to CUCM. Now there's ways that we'll deal with that, either in iOS, which is what you'll see mostly, and then in the one of the videos that I believe is entitled Calling and Called Party Transformation Patterns for CSS CUCM 8 Update. It's a long title. That deals with the new way that we OS. Take your pick. But while there's ways around dealing with that, we will it won't be carried directly over the SIP protocol. Okay, again, SIP is a peer-to-peer protocol just like H323. The PSTN signaling terminates on the gateway, and the SIP gateway or trunk really won't register with the CUCM. There won't be a SIP trunk registration. Now in CUCM, there's only a SIP trunk, not a SIP gateway. I might refer to a SIP gateway. If I'm referring to a gateway, I'm simply saying it's over a SIP trunk as far as CUCM sees it, but it's actually a gateway in the sense that it is a PSTN gateway. Okay, but it still has to be over what Call Manager calls a trunk. Again, pros or advantages for SIP, same thing, pretty much the exact same. 4 logical types of SIP servers. There's a SIP proxy server, which proxies things on behalf of someone else. A SIP registrar server for registration. A SIP location server for locating stuff or keeping track of location. And a SIP redirect server, which, guess what, provides redirect services. If someone moved, if they did a call forward all, it provides things like, hey, redirect over here. They had a temporary move, call forward. All of these are commonly combined into one platform, such as CUCM or CME. However, they are very possible to be spread across physical servers. In larger service provider environments, that's someplace you might see that done. So the session description protocol, since we're going to need to know about that for SIP, let's talk about that. That's IETF 45. It can be used with SIP. I mentioned MGCP. It can be used as a standalone or even to define RTP streams. It is primarily used to define RTP streams. And it's got 3 main descriptions that we'll take a look at: the session description, the time description, and the media description. So first of all, if it's got an asterisk, you see that it's a required attribute. So it's required that we state the V equals, which is the protocol version. And this is how they are I'm going to give you an example here in just a moment, but V equals something, like V equals 0 for version 0 of the message. O equals something, which is the originator and session identifier, and S equals something for the session name. Then we've got the I for session information, U if there's a URI or URL, E if it's an email address format, which we can certainly use for SIP, P if it's a phone number, C for connection information, B if there's information about bandwidth on the lines, Z for time zone adjustments, K if there's an encryption key, and A is it's saying that there are 0 or more session attribute lines. Okay. For time, we have T and R. The time is the required value, and R is basically repeat that line or multiple lines more than once. You know, have more than one timeline. Media, the only one that's required is M, the media name and the transport address. It's important to know title, C for connection information, B for bandwidth, K for encryption because we can encrypt the signaling, the session, or we can also encrypt the media as well. And again, A for just indicating how many lines. There's more than one. So here's an example from a call that I just did. We have version equals 0, O for the originator is Cisco Systems SIP Gateway User Agent. We have 2753 and 6057. Internet, IP version 4, 177.1.254.1. Session, it's a SIP call. C, the connection information that was actually just provided up there at the originator as well. So internet, IPv4, 177. T, 0 and 0. So what was T again? Time. Okay, so we're not specifying any particular time. M for the media. So audio is 18110. That's the port, the RTP port. AVP is an audio video profile. Audio voice profile or audio video profile. I think audio voice profile. And these are basically codes for the codecs or other specific RTP header code fields. So 0, and it actually brings these out. So as we saw for the media, A, 0 or more media attribute lines. And what else do we see there? C was all the media. So back here we actually had C, wasn't required, but it's both in the session, then we have the time, and then it's also in the media as well. Basically saying you're going to be connecting to the same IP address for media as well as the session. It might be different, okay? But these attribute lines are specifying that 0, that 0 up there, is actually PCMU 8000. What is that? 8,000 samples per second, PCM MULA. That's G711 MULA. Okay, 8 bits per second, 8 kilobits per second, G711 MULA. 8 is the code for 8 kilobits per second as the sample rate. G711 ALAW or PCM pulse code modulation in the ALAW companding format. 18 is G729 with an 8,000 bit sample. 18 Annex B is no. So for G729, we are not supporting Annex B. G729 Annex B is VAD. Okay, and VAD is bad. It's also comfort noise generation, CNG. But Annex B is not supported. If it was, it would state Annex B, yes. And then 101, okay? This is a telephone event, also called a named telephone event, which you've seen referred to as NTE. So a named telephone event at a sample rate of 8 bits per second, or 8,000 bits per second, rather. So named telephone event of 101. This is RTP NTE or RFC 2833, which basically using the RTP payload but carrying a data payload, not a voice sample. Okay, so this is a out of band, but sort of in band. Out of band in the sense that it is a DTMF relay. It's not actually audio sampling the dual tone multi-frequency, but it is, it has taken that dual tone multi-frequency, converted it into true relay information, true binary zeros and ones, so that it can be very reliably carried across the network and reassembled without any worry of the codec, the compressor, decompressor, mangling the frequencies in the dual tone multi-frequency. But it's being carried in an RTP packet rather than true out of band in the port RFC 2833, which is again named telephony event, or NTE. So it's saying we support RTP NT. We support that type of DTMF relay. And then 19, notice these are RTP mappings. So 19 is CN. I'm pretty sure this is KPML. So the other DTMF relay that we'll support is KPML. So hey, audio channel, RTP UDP ports 18110, and I'll support G711 mu law, G711 A law, G729, and then for DTMF relay, I'll support RFC 2833, NTE, or KPML. Which do you want to do? Okay, so that's an example of an SDP. Let's take a look at the call flow. So SIP call flow, let's look at delayed offer. First of all, we have our invite. So H323 sent a connect message, SIP sends an invite message. From the invite, the terminating gateway sends back a 100 trying. Hey, I'm trying to locate who you're telling me you want to talk to. Okay, so then it goes ahead and rings, and then it sends back a 180 message ringing. Now, if you've ever worked with HTTP web servers, you note that they've got a number of 3-digit codes. Like, for instance, 404, not found, right? Guess what? SIP uses a lot of those same codes. So 404 in SIP, guess what? It means not found. So somewhat, it's kind of easy to remember, especially if you've ever worked with web servers. But 180, it alerts that it's ringing. The answer comes, and so it sends a 200. So we're at the next stage now. So basically we're connected. That's what the OK is. And it's also going to send the session description protocol with the media offer. Here's what I'm offering. Here's what I support. What would you like to do for media, for DTMF, for VAD, for codec? What would you like to do? So the originating gateway sends back an acknowledgement, an ACK, with the SDP media response. So, okay, I got your offer. Here's my counteroffer. Now, we're going to assume that the counteroffer was basically no counteroffer, just saying okay to everything. If it wasn't okay, then, well, basically the negotiation is, here's the terminating gateway saying, here's what I'm going to offer you. And of those choices, CUCM is either going to say, okay, I'll take this one, or I don't support any of those. And then we're pretty much done because I wasn't offering anything else. Okay. So I've got the acknowledgement with the media response. One or the other side, doesn't matter who, sends a bye, quite simply bye, and we get a, okay, cool, I'm done. And of course it would have torn down the PSTN side before it sent back that okay. So now let's take a look at early offer. Very similar to H323 Fast Start, we're trying to inform the capabilities earlier so that hopefully this can just be a very fast process. So the originating gateway sends the invite, but the SDP is in the invite. Okay? Terminating gateway says, trying, tries to ring the PSTN, tells the originating gateway that it's ringing with a 180 message. PSTN answers, sends a 200 OK with the SDP media response. So here's what we're going to agree on. Acknowledgement, and then the RTP media. Then the bye, and the OK after it terminated the PSTN side. So Nothing revolutionary there. We've already looked at fast start with H323, so it makes sense. Then we have the early media, just like H3. So let's take a look at it. So here we've got the invite, the 100 trying, and then what we have is, so notice the original invite did not have the SDP, but this is the terminating gateway is saying trying, and it's sending a new message, a 183, not a 180 ringing. It actually can send the SDP in the 180 ringing message, or it can send the SDP in the 183 session progress message. Just depends on what each, either iOS gateway or carrier, whatever it's configured to do. CUCM is not configured to support early media by default. However, we can support it. What we have to do so is we can do it globally in CUCM service parameters, or CCM call manager is the service, but the call manager service parameters. And this is known as a PRAC, a provisional acknowledgement. And here's the reason. As the 183 or 180 message sends the SDP, we pre-acknowledge. So we basically go ahead and say, before we even know that they're ringing or connected, because they haven't even started ringing yet, we're going to go ahead and pre-acknowledge that. And for whatever reason, they took the PR from pre and the ACK from acknowledge, and it's a PRAC, is how it is stated. And so it's also referred to as an REL 1XX enable, where we have a PRAC in either the or a PRAC regardless of SDPs. Okay, so there's two ways that we can enable it in CUCM. Support REL 1XXX, or sorry, 1XX, so the 183 and 180 messages support PRAC, whether if it's an SDP, or support it regardless of whether there was an SDP or not. So go ahead and pre-acknowledge all messages like 180. But anyhow, we have the SDP, the session description protocol response, then the ringing answer, and the media response, and the acknowledgement. Okay? So that is, and then the bye and the okay. So that's early media. So let's finally look at Media Gateway Control Protocol. And again, so circa 1999, there's the RFCs if you care to look them up. 3660, 3435, and 3661 are the primaries. This allows for per port control of TDM gateway circuits. That's all the reason it was defined, not for IP to IP, but just for TDM control, TDM gateway control. Uses UDP port 2427 for its basic client server control mechanisms, and it can be used with FXO, FXS. That should say, oh look, it does say FXO, FXS, ENM. For analog, it can be used for T1 CAS, but not E1 CAS. Actually, this support is coming, but I believe it's either 8.6 that it's here. I think it's actually a 9 that it's coming, but it's not here yet. But anyhow, 9 might be here by the time you're listening to this, but it's not necessarily what's in the exam. So T1 CAS, T1 E1 PRI, either flavor, and BRI. If it's used with ISDN PRI or BRI, because ISDN has a layer 3 component, then MGCP, which is an IP, a layer 3 protocol, it backhauls this layer 3 component to CUCM. We'll talk a little bit more about this. Still terminated and controlled by the local iOS MGCP router, but layer 3 is tunneled and sent directly, not mapped and relayed, but it's literally tunneled and sent directly via TCP 2428. So the control is 2427, but UDP. The backhaul is 2428, but TCP. Okay, so 1 digit more, but it's TCP versus UDP. Now there's no dial plan needed or able to be provisioned. This is a true centralized dial plan. And in fact, dial peers are used, but the only reason they're used is to link non-layer 3 components, and that's the reason that I have this asterisk here, is because ISDN PRI and BRI have a layer 3 component, so there is no dial peer. Even T1 CAS, okay, it's a digital POTS trunk, but it doesn't have a layer 3 component. It's got a layer 1 and a layer 2 component. So all of those have to have a dial peer that basically has the port number and something called service MGCP app. Service space MGCP app, all one word. And that links the port to the internal iOS application for MGCP, and that's what allows it to control it. Okay, but MGCP doesn't really control ISDN. It simply tunnels that information to CUCM, and CUCM controls it. Okay, so here's where we have the call signaling for layer 3. The TDM, at least as far as the PRI layer 3, it actually goes through the router all the way back to CUCM. The layer 2 and actually, this is only for ISDN, PRI or BRI. If it were FXO, FXS, there is no backhaul. I just mentioned that. But the layer 2 and framing for ISDN is still terminated locally by the router, and MGCP call signaling handles that. By the way, another thing, MGCP only version 0.1 is supported by CUCM. Okay, if you see version 1.0, don't choose it because it won't work with CUCM. That only works with things like the Cisco BTS soft switch and other industry standard devices. But 0.1 is the version that's supported. Best yet, just not to put any version in at all, and let let iOS automatically provision 0.1, which is what it will do. It'll default to. So some of the pros or advantages for MGCP: a simplified dial plan at your corporate headquarters site where they don't need to be also SRST gateways. If they do need to be SRST gateways, you have to provision the dial plan anyway, so maybe you don't want to use MGCP. MGCP is probably best used at a site local to the CUCM servers that doesn't need SRST. I would argue that it's probably not best deployed at remote sites, but that's my opinion. It does have a simplified iOS configuration, certainly. And one of the things that it does support that's very nice, that H323 and SIP can tunnel, but this probably can provide for more of the enhanced features. Extensions is the word I'm looking for, is the ISDN Q.SIG for PBX integration. The call flow. So I've broken them down into the sections. There's connection commands, audit commands, request command, an endpoint command, that should say actually, oh yeah, look, it does. A notify command, got a little bit too aggressive with my copy paste. And the restart command. So connection commands, this is how they appear, is CRCX. This is create connection, delete connection, modify connection, AU for audit the endpoint, AUCX for audit the connection, and then request notification, EP endpoint configuration, simple notify, and then RS IP, restart in progress. So let's look at the flow, and we're going to look at the difference between a residential gateway and then a trunking gateway. A residential gateway connects to analog circuits out to the PSTN. A trunking gateway connects to digital circuits out to the PSTN. Okay, so an analog gateway, first of all, we're going to send a request for notification, and then it will notify. So we sent a request for notification. We not only got a generic response, yeah, I heard you, but then we get the notify. So it notifies it of its state, what's going on, of that analog connection. And then the master and server, CUCM, because this is a client-server protocol, MGCP cannot talk talk directly to anyone else. It has to talk and be registered to one server, which is called the call agent. Okay, and it does actually show up as registered, or if it doesn't, you have a misconfiguration. It should show up as registered, I should say. So the server sends a create connection. The client sends a create connection response. Yep, I heard you. It creates the connection, rings. Okay, modify your connection, and here's the session description protocol. Here's the media information. We get the response to that modify connection. The RTP media ensues, and then there's a notify when we want to disconnect, and a DLCX, a delete connection, and the response to that. Now, to a trunking gateway out to a digital circuit, it's a little bit different. This is really, I should say trunking really to, something like a PRI, because we have an ISDN Q931 tunneled setup message through the router, not to it, but directly through to the PSTN. Then we tell the MGCP server, MGCP client, the gateway, to create the connection. We have ringing and answering. Then we tell it to do another modify connection and get a response to deal with any other information regarding the media. And then the layer 3 ISDN Q931 connect coming back from the PSTN. The RTP media, and then later when we're done, the delete connection and that response. So let's look at our final phase, and this is just faxing. We're not going to spend very long on it. We're not going to do any demonstrations on faxing. I don't have any of the gear in my rack, but as long as we understand the basics of it, then you should be good for the exam. And the idea is that faxing and modem use digital data modulated, but into very high frequencies. And as we've just looked at, voice over IP was really designed for human male and female voice speech frequencies, not high frequencies beyond what human speech not only can sometimes audibly hear, sometimes in the audible range, sometimes not, but certainly, it's designed for up to 4,000 hertz, fax or modem tones, and then as a voice gateway, and then retransmit those as out-of-band data. So the routers, the voice gateways can hear this frequency, but it's just the codecs, the compressors, the decompressors weren't really necessarily, built or designed to sample and carry samples in those audibly sampled frequencies. So because these routers can hear, one way is to terminate this and to just convert it into reliable ones and zeros and send it as relay. This is called fax or modem relay, and there's a few different kinds. There's either the Cisco proprietary fax relay, and there's also the ITU-T fax relay called T.38. Now, T.30 is the ITU-T spec for just regular POTS fax transmissions. Okay, so when we speak of T.30, that's faxing over the actual POTS lines, just like if we're speaking of H.320, that's ISDN over PRI. But if we're speaking of T.38, that's fax relay over IP. Okay, so another way is to terminate the modulated fax tones, convert the messages into email, and send them to a recipient via SMTP. This is what's known as a store and forward type solution, also called an on-ramp or off-ramp solution. And another way yet is to send those modulated tones in the actual sampled codec. Now this is only going to work with G711 or G722. Okay, but this is called pass. We have, RTP is sent over UDP. So if we drop even 1% packet loss, well, we're going to lose some of those fax tones and we're not going to get our entire message. So pass through is what you want to avoid. T.38 fax relay is what you want to move towards or use. Cisco Fax Relay as a proprietary is a backup option. Store and forward can be used in certain circumstances. So let's look at fax pass-through. So here we've got the initial T.30 fax tones, and that's going to trigger the initial. So here we've got a fax machine on the left. I guess I should set the stage. A voice gateway in the left middle, a voice gateway in the middle right, and then on the far right, another fax machine. Whether these are CUCM as gateways or just routers, we need to get them from one side, which is hearing the information and sampling it. Well, either sampling it and turning it into a voice over IP or hearing it and turning it into relay. Right now, we're sampling it through pass-through is what we're talking about. So sending it in the actual G711 codec and then getting to the other side and remodulating that to audible frequencies for the terminating fax machine. Okay, so the fax tones are carried in the RTP codec of G711. The CED tones, which CED is basically endpoint identification sent through modulated tones and endpoint identification of the fax machine. Okay, faxes can be reliable in the sense that they send tones that indicate they are who they say they are, more or less. The answer from the other side, similar, but that's a named telephony event. This is a named signaling event. We have the NSE accept. There's where we now know that we've heard tones that tell us this originating gateway, okay, this is a fax or modem call. It's not a standard voice call. So we need to dynamically change our codec on our dial peer into G711, make sure VAT is disabled, make sure echo cancelers are disabled, because remember, echo cancelers are going to cancel within the echo return loss area, whether it's 32 milliseconds long or 64 milliseconds long or 128 milliseconds long. They're going to cancel out signal milliseconds. Well, faxing might have very similar tones, if not the exact same tone, coming from one side and going from the other side at the same time. It doesn't mean it's echo, though. And an echo canceler will kill a fax. So that's one of the things that this does, is it disables the echo canceler. And then the fax call can proceed sampled in the G711 RTP media payload. A much more reliable way, Cisco Fax Relay. Okay, so the T.30 terminates at the router. The router sets up a VoIP call to the other side, and T.30, the terminating gateway, signals the terminating fax through T.30 to set up the call. The CED tones, the endpoint identification is what that is. This fax machine supports something called Group 3, which is the standard, was the default standard for a while, or something called Super Group 3, which could kind of loosely be analogous to a modem back in the day between V.90 or V.92 standards. So can I transmit at a much higher rate of speed? Okay, so sending those machine capabilities. Then the originating gateway will switch over to fax relay. So it's going to take all those tones and all the subsequent tones that it's going to hear for the actual fax, and it's going to turn those into reliable ones and zeros, and it's just going to transmit those out of band in the actual Cisco proprietary fax relay. Okay, for the codec to deal with the specific relay, and there's a download. We send the download complete, the acknowledgement, and then the fax relay is established, and we send the message out of band in that reliable relay. Now, the ITU T38 does it a little bit different, very similar in the setup, the CED and DIS tones, but then instead of what we saw earlier, there is something called a mode request that's sent, and of course an acknowledgement. We close VoIP, and instead we open a T.38 channel, and this is the best thing to use if everything supports it. and we have the fax relay established, and we send the message. Well, if we've got, let's say, a small office, and maybe we've got, let's say, CME is here, and we've got CUE, Unity Express, or Unity Connection can also handle this. And we've got a fax machine, and we're going to do on-ramp, off-ramp. So first of all, a fax call comes in to a POTS dial peer, and the router triggers a TCL, tool command language, script running on the router that listens to all the T30 tones, and instead of relaying them anywhere, turns them directly into an email, packages them up, sends them in an email, and in a PNG, portable network graphics, or or attaches that to the email, uses the information from the T30 as to who that message was destined to, and puts that as the to field, who it's going to for the email, and sends it out through an MMOIP, a multimedia over IP dial peer, and emails it onto the, either directly or typically to a voice messaging, a unified messaging server such as Unity Express or Unity Connection. Okay? That's called an on-ramp fax gateway. An off-ramp fax gateway does exactly the opposite. The user emails the message to the router or to Unity Connection, Unity Express. It turns it into an email, sends it to the router through inbound on the MMOIP dial peer, and then outbound a TCL application that's embedded in iOS, and they're already by default. All you have to do is activate it or call it from the POTS dial peer. And then the off-ramp TCL script, which is a separate one, which looks at the email, disassembles it, grabs that PNG, and modulates that information into tones, into audible frequencies, and sends out a T30 fax message to the fax machine. And I actually lied. There are 2 more slides and then we're done. So I want to talk about real quick the ITU-T G.114 spec, which talks about acceptable one-way delay or latency. So before in CCNA, we had mentioned that less than or equal to 150 milliseconds is what we want one way for delay. Okay, less than or equal to. This is what's defined in the G114 spec as acceptable for most people. From 150 to 400 milliseconds, this is defined as acceptable only if the administrators and or the users, basically the administrators, are aware and inform the users of the transmission time and the fact that it's going to get into a sort of a walkie-talkie type conversation where I might have to say over. Probably, hopefully not quite at that level, hear it before they're going to be able to respond. So I'm going to need to wait to listen to their response. I shouldn't expect that if I don't hear anything, the person has just stopped listening to me or hung up. And then greater than 400 milliseconds is typically unacceptable for most people. However, some cases may warrant, such as satellite-based communications. Now, a lot of advances have been made in satellite communications, but we're going to look at the next slide and the last slide as delay types. And one of those delay types, as I'll just look, is propagation delay. So propagation delay is the propagation, the time that it takes to propagate or send out over a given medium the signal. So if I'm sending it over a satellite, I've got a fixed, a minimum fixed. Now it could be variable beyond that. I don't remember exactly what the delay is. But the point is that the law of light propagation says that nothing can travel faster than light. Einstein's theory of relativity says maybe different. I tend to agree with the latter, but regardless, we haven't broken the sound of light yet. The sound of light? The speed of light, sorry. It's been a long module. But we're not going to be able to send out to a satellite orbiting at 22,000 miles orbit around the Earth and then back in less time than it's going to take to do that. Okay, so compression techniques help, and there's a number of other things, but regardless, that might be a case where beyond 400 milliseconds might be acceptable for military communications or something like that. But anyhow, these are the types of delay. We have DSP delay. That's fixed. That's going to be 18 milliseconds. So if we're talking about 100, we can't just do a ping. We have to take more into account. First of all, there's going to be 18 milliseconds for DSP. What is it? Sampling, quantization, encoding, and optional compression. Then we have the packetization or processing delay. This is also fixed. It's going to take 30 milliseconds to turn that into an IP, RTP, UDP, IP packet. Then the queuing delay, the egress queuing on the hardware queue, the TX ring. This is going to be variable, depends on the congestion. Serialization. This is fixed. How long does it actually take to turn that signal into electrical pulses for the actual line? Serialize it. It's fixed, but it depends on the medium. So the faster then we have propagation delay. Again, this is a variable, depends on the distance. And then we have dejitter buffer. So at the other side, the receiving side, they're going to have a dejitter buffer to try to deal with the variance in delay, the differences in the different delays. So this is a fixed 45 milliseconds. So right in here, we can see that we already have, let's see, fixed 45 and 30. So we've got 75, 85, 90. We've got 93 milliseconds already. So that limits us quite a bit to what we can allow. Now, this is one way. Okay, it's not necessarily round trip. So you have to take that into account. When you ping, it's a round trip. So just important to take into account when you do your delay budget, you create a delay budget and you decide if voice over IP is going to work well or be at a slightly minimized impacted level.